two light bulbs in there. The bigger the diameter of the bulb, the more light is swallowed up by the bulb itself. You don't get as much. If you had just a line of light, it'd be more efficient. And so when you get into, that's a T12, you get into a T8, or even a T5, which is the new 5/8 of an inch diameter. And those are the brand new ones you'll see. Those are even more efficient. Electronic ballasts are more efficient than the magnetic ballasts, old-fashioned ones. The T5s are much more efficient than T8s and T12s. And then you get the new, very highly polished reflectors. That means more light's going to hit the surface down here, because who cares about the fixture being bright? I don't care. Backside of that bulb looks pretty bright up there. Could care less. I don't need that light. I need it down here. So you look at all the things, pack it all in, and these brand new T5s with the nice reflective fixtures are probably twice as efficient as your old lighting. It's one of the best investments you can make is to upgrade your lighting of your building. What else happens when you do so? Strange things. Absenteeism goes down. You have a building with 300 people in it, office building, people doing records all day, and you go relamp it, and your absenteeism goes down. They've proven that. It's like, why? Who knows? People consciously come to work because the lighting's better? Don't know. But less people call in sick. In fact, so much less that it in effect paid for the lighting change by itself. Change in absenteeism rate. It's like a little bizarre, but still it can work. So, many reasons to actually get your lighting correct. Now, what else goes on in this thing? How do I size a range? Well, they're going to tell you in here. A range, a stove, what else? Whatever you want to call it. They claim that not all of it is on at the same time. My first flippant answer is, you morons, what about Thanksgiving? Think of your stove, range, oven, about Thanksgiving. All 4 burners on? Yeah. The oven on? Yeah. So is everything on? No. What about the broiler? Do you usually put the broiler on and the oven's on? No. How about all the burners? Are they on full throttle? Usually not. One of them's simmering, one's a little boil, one's this, one's that. So when you look at the real full load on there, even during Thanksgiving, it's not fully loaded. Holy cow. So they have a little requirement. If you look at the nameplate rating, range, stove, nameplate, they basically say if it's up to 8.75 kW, it's 80%. Now, 8.87, believe it or not, to 12 kW, it's 8 kW. 12 to 27 kW, it is 8 kW plus 0.4 kW of the difference above 12 kW. So it's a little formula. Now, what about what units? I'm writing kW here, but when it's a totally resistive load, like a stove would be, electric stove, how else can I write a kW? Volt amp, right? So you can also volt amp for totally resistive load. So I can go to the nameplate of a stove, and that's why you have to have some knowledge of what people are buying these days. If I'm a home builder and I'm the electrical contractor and I'm building, 1,500 square foot houses versus 3,000 square foot houses, the different demands and desires of people in the different markets tell me what kind of stove I'm going to put on there. These are real nice fancy ones or a plain what they call contractor grade, which means the cheapest thing in Home Depot. It depends on what you're buying for what market, but you can go through the nameplate and figure out exactly the demand predicted by the NEC, the National Electric Code, and what you have to size the wiring for. So, there's an example problem in your homework about that. In fact, what if we have a, well, right over here. Here's an example, a 16.2 kW range. Let's see. In fact, did I do that right? Yeah. Okay, so where am I in this market here? 16 kW, somewhere up here. So my minimum is 8 kW because it's above that range right there. So I have 8 kW plus the difference, 0.4 kW times the difference of 16.2 minus 12. So 8 kW plus 0.4 times 4.2, which is 1.68. So 9.68 kW. So 9.6 kW, 68 kW, which is equal to 9,680 watts, or 9,680 volt amp. What's the service into a stove typically? 240. So I take this and divide by 240 amps, and then I end up volts. Okay, and I end up with approximately equal to a little bit over 40 amps. 40 amps plus. And that's how I size my breaker. So if I'm just over 40 amps, then what kind of breaker do I put in?
60, where do they go?
I think it's 50 on that side. On 240, you go 30, 40, 50. Okay, so a 50 amp breaker would be on that. Now, here's the other part that's crazy. I'm sized for 240, but what if my neighborhood's 208? Anybody got a calculator? 9,680 divided by 208?
46.5.
Right, 46.5 amps. So if I'm at 16 instead of 16.2, and this ends up at 9,600 divided by 240, that's right at 40 amps. So I go, hell, I can save a few bucks. I'm put 100 houses in here. I'll buy 40 amp breakers for all this. So I buy a 40 amp breaker, come in and misread the whole development plan and find out they're having a 208 transformer in there, and it's actually 46.5 amps. Oops. So, just the change of voltage, you have to know what's going in the development. So in fact, our development is so old, they have a couple of machines in the back of the development, a couple of old air conditioning systems that run off 460 volt three-phase, which is really old school. Like three-phase for a residential environment, it's kind of crazy. So, you have to watch the voltage and make sure you have that right. Small differences can mean a lot. One's a 40 amp breaker barely, the other is a 50 amp easily. So that's an example of how to size a range.
So what they're saying here is it's max at 16.2, but they say you're never use it, and 9.68 is most of it.
Right. This is what the range nameplate is, right? That's how much it could draw with. It's got to be sized for safety. But when it comes to how I design my house and everything else, I'm only going to say that I'm going to have a 46.5 or a 40 amp draw on that at any one particular time. Because what you're going to end up doing through the whole 9 yards exercise is to go through all this and say, I need so many amps for this, so many amps for that, add all this up and say, here's my ampacity for the whole house. That's the story. That's why you go through the whole mess. Everything is a judgment call based on the National Electric Code, and it tells you what you put down for all these things, you add it up, and I end up with so much. Now, what are the minimum requirements? Ag buildings, what are we allowed to have as a minimum circuit breaker panel in an ag building? We did that last chapter. Monday morning after break, let me think. 60 amps. Okay, minimum for a house, a residence, is not 60 amps. It's 100 amps. But as time has gone on and our houses have gotten bigger and bigger, you know, the average house size in 1950, right after the war, was like not quite 1,000 square feet. Average. Now, the average house size now is about 2,500 square feet. So since we know we have people that live in smaller houses, somebody out there is building some huge houses. Okay, so our ampacity in our buildings, our residences, have gone up to about 300 amps. Typically, you know, we start off at a minimum of 100 amps. And probably when my house was built in '69, it was 150 amps. And probably mid, let's see, 60s, 50s, and late 70s to 80s. 80s, you probably end up with 200, 250 amp services. And I contend that'll probably go back down. The arc is downward, because as things get more and more efficient, you're not going to need that much amperage anymore. So, all right. So if you go through all the stoves and that kind of stuff. Now,